All right, good evening. Welcome to the Science Cafe. I'm subbing in for Sarah Wyatt today, who couldn't be here. Just a couple of announcements before we begin. Next week on November 12th, we'll have a cafe conversation by Jeff DeBelco, who will be talking about the environment, what security got to do with it. And then on November 19th, Dina Lopez from Geological Sciences will be here for a Science Cafe. And tonight, Doug Clowe is going to talk to us about the dark side of the universe. Thank you.
Okay. All right, well, good evening, everyone. So what I'm going to be doing tonight is kind of, most people would call it sort of the edge of science. I'm going to try to convince you that something that we have no idea what it is and we have never been able to detect it actually exists. All right? So collectively, we're going to talk about what's known as the dark sector. And the dark sector makes up 95% of the universe. All right? Before I begin, I always like to start with a very simple question. Anyone here know how big the universe actually is?
It's expanding.
Yeah, it's definitely expanding. But anyone know how big, right? How many galaxies we can see? Anything on that order? Because you always see pictures on the news and stuff like this from the Hubble Space Telescope of galaxies. But few people understand exactly how small those images really are. So I'm going to start with this picture, which is a picture taken with a fisheye lens on a mountaintop outside of Arizona. So you're seeing basically the horizon is all around. And the looking straight up, this is as if you were lying on your back, just looking up at the stars. All right, this is the plane of our own galaxy, the Milky Way. The center of the Milky Way is right there. That's a tree. These are streetlights from Tucson and a suburb. All right, so this is what you should be seeing if you go out at night and look up at the sky. For this to really happen, you're going to have to get out into a dark place away from all streetlights for about half an hour for your eyes to get really big. But this is about how many stars you should be seeing out there. Right? If we're going to zoom in to a region that's about 10 degrees on a side, 10 degrees is if you hold out both of your fists and sort of look at it. All right, that's about 10 degrees. All right, then we're going to, in a movie, start zooming in, and we're going to wind up at an image that's 1 arc minute. And 1 arc minute is 1/60th of a degree. If you hold out a sharpened pencil at the end of your arm, that's about 2 arc minutes. So the image that we're going to wind up with on the sky is half the size of a sharp pencil tip held out at the end of your arm. All right, so we're going to start here, and here we have Orion that sort of gives you an idea of the scale. And mostly what you're seeing here are stars in our own galaxy. All right. I'm going to zoom in. We're up to about a degree now. We're starting to run out of bright stars, so we're going to transition to a little bit deeper exposure and start looking at some fainter stars. You're going to start seeing a few galaxies here and there show up. They're going to look like the more extended things. We're down to about 10 arc minutes. We're going to keep zooming in, and now we're going to transition to an even deeper image from the Hubble Space Telescope. Right? And we're going to stop right about now, and this is 1 arc minute on the sky. So this is half of a sharp pencil tip out at the end of your arm. Right? Mostly what you're seeing here are now galaxies. These things that have the plus signs on them, those are stars. The plus signs are just an artifact of the telescope. You have to have something holding up the secondary mirror, and so you're seeing light reflecting off that. Pretty much everything else you see here are galaxies outside of our own. Right? Most of these galaxies are about the same size as our own as well. Right? To estimate how many galaxies are in the observable universe, all we have to do is basically count the number of galaxies in this image and then simply multiply by the ratio of the area of this image to the area of the full sky. If you do that, you come up with a number that's there's somewhere around 10 billion galaxies if we could get this quality imaging over the entire sky, and we could remove our own galaxy from blocking our view. Right? Our own galaxy, when we do a census, has something like 100 billion stars in it. And that's a fairly typical size for a galaxy. So you have 10 billion galaxies, each one of which has about 100 billion stars. You multiply those two together. Within our observable universe, there's 10 to the power of 21 stars. Right? That's 1 sextillion. I had to look that up. Right? So 1 with 21 zeros behind it. And I say it's our observable universe because we have learned that the universe is expanding, which meant it might have began about 13.7 billion years ago. And we're only seeing the stars whose light has been able to travel to us over that intervening 13.7 billion years. Within that bubble, we don't see an edge. So we know a minimum size of the universe. We don't see a maximum size. And for all we know, the universe might be infinite in size, but we have this bubble which we can see and can learn about. All right? And what we've learned is everything that you're seeing here makes up less than 1% of what's actually there. All right? When we do a census, all those stars actually wind up about 0.5% of the total mass. There's a lot more hydrogen and helium, just normal matter, that's never gotten dense enough to fall into stars. It's about 8 times more massive. And that's this stuff here, which is about 4% of the total mass. All the heavy elements, the stuff that's not hydrogen and helium, is about 0.03%. And that's because these are things that didn't exist at the beginning of the universe and have been made in stars since then. And finally, there's an extra type of particle called a neutrino that is made in nuclear fusion events. And that makes up somewhere around 0.3% of the total mass. You add all that up, and you get to a number that's slightly less than 5%. The other 95% is split up into 2 parts. You have dark matter and dark energy. These have been named because we don't know what they are. All we know right now, really, is that they don't interact with light, and thus they get the dark name. All right? And I'm going to spend most of the rest of the talk talking about dark matter, because that's what we have really good evidence for, and I can sort of explain how we know it exists, even though we don't know what it is. And then I'll end with a little bit about what dark energy is, which is most of the universe, for which we don't even really have a good idea right now what it is. All right, so dark matter itself has been known about, well, I should say yes, everyone thinks of that when I talk about dark matter. As far as we know, nothing to do with dark matter or dark energy. All right. The other thing people often think about with dark matter is this, the Horsehead Nebula. That's not dark matter. That is just normal matter in the form of dust. I cannot see that.
Speak louder.
Speak louder, okay. This is just normal matter in the form of dust. It's absorbing light that's behind it, and so that's why you see this, it's just a shadow. Dark matter doesn't interact with light at all, as near as we can tell. So if a cloud of dark matter is between us and a star, we still see that star without any problems whatsoever. The light just goes straight through the dark matter, which is part of what makes it so hard to find. All right, so how do we know about this? It began with this guy, Fritz Zwicky, one of the more colorful astronomers in history. He found it in 1933, and what he did was he took an image of something like this, which is a cluster of galaxies. And this is a group where you have thousands of galaxies that are all in a common gravitational pull. And so they're sitting around orbiting each other. And what he reasoned is if you could go in and simply using a Doppler shift, a physics technique in which the wavelength of light changes as something is moving towards or away from you, same thing that cops use to catch you on the freeway, you could look at how fast all these galaxies are moving and look at the fastest moving galaxies. And since this thing is a structure on the sky, that has to be less than the escape velocity of this thing that's holding it together. And so once you compute that, you can compute a minimum mass for this structure. So he did that and realized that the minimum mass for this structure, holding all these galaxies together, was more than 100 times the mass of the stars that he saw. Unfortunately, he was also not one of the most well-liked astronomers around. So this realization at the time, there was only really 2 clusters that they could do this on. They realized that both of these had the same problem, but they also had a lot of other problems trying to understand things like how the sun worked. And so this sort of fell by the wayside. And for about 40 years, not much else was done on it. All right. In 1970s, we got X-ray technology, where we could launch satellites and look up at much higher energy light. And when they looked at the same clusters, instead of seeing galaxies, they saw that, a big blur. And if you superimpose the 2 on each other, you see this big blur basically sitting amongst all these galaxies. This blur is all that hydrogen and helium in this region of this cluster that never fell into stars. So what's happened is the gravitational pull of this cluster has pulled in all this free hydrogen and helium that never got dense enough to form galaxies and stars. In the course of falling in, it heats up, and it gets up to a couple 100 million degrees, and that's hot enough that it just starts emitting X-rays, right? So this free hydrogen and helium is about 10 times more massive than all the stars that we see. So in terms of the normal matter, the stuff made out of protons and neutrons, it's this X-ray cloud which has most of the mass. But if you would take that new mass, which is now 10 times higher, and compare it to what we need to hold all the galaxies together, it's still a factor of about 6 to 7 too low. So we still need most of the mass to be in something that we don't see. We can extend this in the other direction and go look at radio waves, and we don't see any additional mass at all. So whatever it is that's holding this is basically invisible to light. It doesn't seem to emit light, and it doesn't seem to absorb light. All right, well, about the same time this was realized, people went and were able to look at individual galaxies as well. Right, so here's a typical galaxy. They have these disks. This is very similar to what we think the Milky Way looks like. And the characteristic of these disk galaxies is they're all spinning. And they're all basically in fairly circular orbits going in the same direction in this disk. And so we can again use a Doppler shift and now break it up and look at the Doppler shift as a function of radius coming out. And we can figure out the velocity that this thing is spinning at as you go outwards in distance. Right? If you do that, you get this measurement in which all these galaxies, once you get outside of about a central 2,000 or so light years, all these disks spin at about the same velocity. Right? Well, we can use first-year physics to relate the velocity that these things are moving at, because that's just kinetic energy, to their orbits, and we can work out the mass of the gravitational field that they're sitting in to orbit at that speed. So then we can take all the stars and all the gas that we see here, and we can ask, okay, if that's the matter that's present in this galaxy, how fast should all these stars be orbiting around? And so here's what we measure. Here's what the gas would deliver, and here's what the stars would deliver. Right? So for the central, again, couple thousand light years, the stars actually do a pretty good job. But once you get outside of a couple thousand light years in radius, you should be seeing the velocity of the orbit slow down, and yet they're staying constant. And that means that you need this extra mass to be showing up as you go outwards in radius as well. So we need it for the galaxy clusters to hold them together, and we need it for these galaxies to explain how fast they are rotating. Now the problem is there's actually two possible explanations here. One is that we're just missing some mass, some form of dark matter. The second is we've only measured the way gravity works inside of our own solar system. Everything outside of our own solar system is basically a model, right? We can say it seems to be obey what we see in this other system, but we've never really measured it directly on scales of 10,000 light years. We've only measured it on scales of under a light year. And so it could be that when you jump up that far, maybe our law of gravity is only an approximation. Maybe it changes as you go out to even larger radius. So with both this observation with the spinning galaxy and this observation with all the mass and the fast-moving galaxies, it might not be dark matter at all. It might be that we don't understand the way gravity works on really large scales. And that's where it stood basically from the time Zwicky invented or discovered this, right? Those were the two conclusions that he drew. And up until about 10 years ago, those were the two conclusions that you could draw. Because the problem is, any dark matter that's here is in roughly the same location as all of the protons and neutrons. And so we have no way of knowing which of those solutions is correct. Right? However, it does give us one hint due to the fact that this inner region here is well described by stars. So in physics, you start off with a large cloud of something, and you allow gravity to take over, and it starts collapsing inwards under a gravitational force. As you fall inwards, you start picking up speed, right? The same as a ball being dropped towards the Earth. Eventually, you go fast enough that you can go into an orbit around the thing which is pulling you in. That's something called virial equilibrium. All right? Once you reach that, unless you have a way of getting rid of your velocity, you're going to stay in that orbit forever. The dark matter, because it can't interact with light, The only way it could get rid of the energy of its orbit is if it could collide with something, right? It seems to be staying out at large radius, which would suggest that this dark matter stuff, whatever it is, also doesn't collide with either itself or normal matter very often. The normal matter, the hydrogen and helium and the heavier elements, do emit light, so they can get rid of energy that way, and they can collide with each other, right? You just wave your hand through the air, and you're colliding with matter. As a result, they can get rid of it of energy, and so they can collapse down further. And this is why normal matter can go all the way down to stars. And you can get a very dense central core of this galaxy, which is explained just by the stars. But the dark matter has to stay out at larger radius. So dark matter should only affect things at large radius because it can't collapse down any further because it has no way of getting rid of its energy. Which also explains why we don't have any dark matter, or at least no significant amounts of dark matter within our solar system. Right? All right, now if we could somehow take this system and put it into a physics lab here on Earth, how could we determine whether dark matter was there? Well, the simplest way, right, you take something like this, you put it in a centrifuge, you break it up by different components, you pull the components out, you weigh them, you figure out how much mass is in each component, and if at the end you have something left in your test tube that you can't take out and has a large amount of mass, you know you just encountered dark matter. All right? That's what's happened here essentially for us. This is one of these galaxy clusters. All right, there's one galaxy cluster right down over here. There's a second galaxy cluster over here. In pink now is shown the X-ray emission. So these are these super hot gas clouds that come from falling down the potential wells of these galaxy clusters. You notice it's not sitting on top of the galaxies anymore. In fact, it's sitting between the two galaxy clusters. The other hint is that shape right there. Anyone recognize that? You've probably seen that shape before when looking at pictures of things on Earth. I'll give you a hint. Think fighter jets. What you're seeing is a supersonic bow shock. The same sort of structure that you see whenever a fighter jet goes faster than the speed of sound. So what's happening here is this gas cloud has moved through that gas cloud. And not only do we know which way is it going, it's going in this direction. From the shape of this bow shock, we can compute the temperature and density that we measure for this cloud from the X-ray data. We can compute the speed of sound. We can compute the Mach number of this bow shock. The shape of it depends on the Mach number. That gives us the speed that this thing is moving at. So we know that this cloud is moving through this cloud at about 3,000 kilometers per second, which is also roughly the infall velocity of something falling, starting at the edge of this cluster and just falling in due to its own gravity. So what's happened here is this cluster started off down here, and over the age of the universe, it was pulled in by this guy's gravity, missed it ever so slightly, got slingshot over, and when this happened, these gas clouds here, they're so hot that they're fully ionized. So it's electrons and protons kind of isolated, and so they interact with each other with the electromagnetic force, which is a very strong interaction. The stars are in the galaxies. In galaxies, stars are 1 million or more times smaller than the typical separation between them. And so even if galaxies pass through each other, the stars almost never collide. And so during this interaction, the galaxies can go through with barely any slowing down at all. The gas clouds, however, trade momentum the same as two fog banks would if they tried passing through each other on Earth. So we're now seeing this about 100 million years after that collision. And during that time, the galaxies are now moving apart faster than the gas clouds are, which is why you're seeing the gas clouds between the two. Remember that the gas clouds have roughly 10 times more mass in them than the galaxies. So nature has now given us our centrifuge. We've separated out the two types of matter that we can see in terms of the stars and these hot gas clouds. And if the answer is dark matter, well, we know dark matter doesn't collide with itself very much or with things because it has to sit out at large radius for these galaxies. So they should be going through the same as the galaxies do. If the answer is we don't understand the law of gravity, well, this is where 90% of the mass is located. So the gravity should be with the 90% and not with the 10%. It'd be almost impossible, in fact, to explain a force law of gravity in which 10% of the mass is producing 90% of the gravity. All right, so sort of as an animation, just to show you, here's a mix of what dark matter and gas would do. They go through each other. The smaller one basically trades momentum with the bigger cloud. The dark matter and the galaxies keep going, and at the end, they get separated. All right, so how can we measure the mass? All right, well, all the ways that I've been talking about, the rotations and the velocities and that sort of stuff, aren't going to work at this point because we knew that these two things are colliding. So they haven't had time to settle down to the point where they're orbiting around each other. But there is a technique that we can use, which is called gravitational lensing. This comes from Einstein's theory of general relativity. And in general relativity, gravity is not a force pulling on you. It's a warping of space-time. And light will travel in a straight line always. But if you're traveling in a straight line on a curved surface, you start bending your path. And so that's what's happening here, is this foreground cluster is warping the space-time here. So the light from this background galaxy is still traveling in a straight line, but relative to us, it's actually curving. And it comes in at this angle. Due to the way that the curving works, you also stretch the background galaxy's shape tangentially. Right? It can go that way. It can also go this way. Right? Now, we can only see the light as it approaches us. So from our point of view, the galaxy is not here. We see an image of the galaxy up here, and we see it being stretched relative to the position of here, and you'd see the same thing down here. Right? This is called strong lensing. Right? Here's an example of it. So here is a central galaxy from a galaxy cluster. All these orangish things are the galaxies that are part of the clusters. Right? And there's two different galaxies here that have been lensed. One of them are these star-looking things. That's actually a quasar. That's a central black hole of a distant galaxy that's currently absorbing a lot of material, and in doing so, it's emitting light from that material that it's currently absorbing. They can be very bright. So you have one image there, you have one image there, one image there, one image there, and it's kind of hard to see, but there's a very faint image sort of in the middle of that galaxy as well. Those are all actually the same quasar. You're seeing 5 different images of that same object. The object itself is actually located about right back there, but the light that would be traveling normally in the straight line to us from it is getting bent by the gravity and going off somewhere else, so we don't see it. All right? If you look really carefully, you might be able to see an orangish sort of extent behind the quasar. That's actually the galaxy that it's sitting in. And you can also see the orangish extent there, it's there, and it's very hard to see, but it's kind of right there too. Right? The other one is this guy, which has one image there, one image there, and one image there. And those 3 are all the same galaxy as well. And so by taking these positions, and we can learn what is the distribution of mass inside of here. Right? It's a very powerful way of measuring the mass. The problem is it requires objects to be sort of back there in just the right location. And most of the time, there are no objects there, because you can see the sky is black. So most positions which you look at, there isn't a galaxy, and so most clusters don't have this strong lensing feature in them. Right? So we have to look instead further away. So here's a simulation where we take a cluster galaxies and we move some background galaxies behind it in a screen. And you can see we put it in a high enough density that you usually will have some amount of strong lensing around here. By the time you get over to here, these galaxies are still being gravitationally lensed. They're still being deflected away from the center of where they were located, and they're still being stretched, right? You can still see that they still have this arc curve to them going around it. Right? That's because we took relatively circular galaxies for this. Galaxies, unfortunately, all have shapes, right? These are the foreground galaxies. You can see that they tend not to be round. And we have no way of knowing what the shape of a galaxy was before it was lensed. We only get the combined lensing plus shape. Right, so if we take another simulation, here we have an invisible cluster causing the strong lensing, which you can see by eye. By the time you're out here, gravitational lensing is still going on, and it's still stretching the galaxies. But it's stretching it less than the intrinsic shape of the galaxies. So by eye, you can't really tell what's going on anymore. Right? But if we take this little thing over here, which is about 10 times the strong lensing radius away, and blow it up, Here are all the individual galaxies that we put into the simulation, and the ellipses are basically showing their ellipticities, which you can measure. If there was no gravitational lensing, galaxies should be randomly oriented, because the galaxies are very far away from each other in 3 dimensions. And so you should be able to average over all the shapes and get something that's essentially round. If there is gravitational lensing, you can average over all these shapes, and what you should have is an ellipse with a major axis, which is basically perpendicular to the radial distance from this cluster. You do that in this box, and you get a major axis that looks like that. It should be a major axis that looks like that. And the small difference there is because we have a finite number of clusters, or a finite number of galaxies, and therefore we can't completely average it down to something that would otherwise be perfectly circular. Right? So when we're doing weak lensing, we don't look at individual galaxies. We sort of average over galaxies to look for a coherent pattern that is not consistent with it being randomly distributed, but instead saying that on average, your things are being stretched in a certain direction. And we can do that in this box. You can do that in this box. You can do it down here. You can do it down here. And we can build up as both a function of radius and angle how this stretching looks like. And from that, we can go back into the math of GR and work out from that stretching that we see as a function of radius and position, what is the distribution of mass in this invisible cluster that's causing that deformation of the background galaxies. Right? It's a very powerful technique because unlike the strong lensing, which may or may not be there, the weak lensing is always present because you're covering a much larger area, and so you always have background galaxies behind it. And you can also go out much further in radius. And so we can get the mass of the cluster out to much larger distances than we can with just the strong lensing. So to show how this works in practice, here's an image. This is from what's known as the Very Large Telescope, which is an 8-meter telescope down in Chile. This is about 2 hours in 3 different passbands to get this image. So basically a full night on a very expensive telescope. The orangish things are cluster galaxies. Right? This cluster is located, well, the light has been traveling to us for about 5 billion years. We're not interested in that. We're interested in all the galaxies whose light has been traveling to us longer than that. And so if we go in and look at this cluster in sort of black and white, in just one passband, we don't care about the bright big galaxies, because those are either part of the cluster or between us and the cluster. To do the gravitational lensing, we look at all the small galaxies, because those are the ones that are on average going to be further away. So here you can see the little sort of paramecium-looking things are the ellipses from measuring the shapes of these galaxies. There's one complication, which is that thing there is actually a star, and stars should be small points on this image. It's not a small point because the atmosphere has basically blurred everything and the telescope can't focus perfectly. And so the light, instead of being a point, has been smeared out over a large area. That's been happening to all of these galaxies as well. So if we don't correct for that, everything will look a little bit rounder than it should. And that would change what we measure for this stretching. Right, so we have to correct for that. We have a lot of algorithms to do that. If you wish for a really boring talk, I'll explain those algorithms. But otherwise, just trust me that they work. And when you do that, we can then recover those stretching as a function of position on that image. And using those GR equations, work out what is the underlying mass. Right, so here we have the galaxy cluster again. And the contours here are now indicating the density of the mass in that region. So read these contours as you would an elevation map on a hiking or elevation on a hiking map. Every time you go across a contour, you're going into a denser region. Right? So you can see that there's some structure here doing that, but then as you get into this cluster, right, you have increasing amounts where as you get to denser and denser material, you're going into the center, and the densest part is sitting right on top of that central galaxy. Right? So with this technique, because we've been able to cover the whole image, we can not only measure or how much total mass there is in this image, we can also measure how it's distributed within portions. Now, we can't get it perfectly because remember, we have no way of knowing what the shape of the galaxy was beforehand. And that effectively gives us what's called a noise term, which means it adds some uncertainty. And so, for instance, this little closed loop down there, we don't really know, is that really some mass that we've detected down there? Or is that just an artifact of these galaxy shapes being sort of randomly distributed? Right? In similar ways, we're not completely sure about this stuff right here either. But this stuff is detected well enough that we know that we found the cluster there and that the mass really is distributed in that direction. all right? So that's what we do with gravitational lensing, and this allows us to measure the mass of something irrespective of whether it's in an orbit or not, because we're actually measuring the gravity directly. So we can now go back to our system here, and we have a very nice deep image. In fact, if you might notice, that star looks completely different from that star, and that's because this is from a very deep ground-based image. That's from the Hubble Space Telescope. I've just sort of put the two pictures on top of each other, all right? But we can take all these faint galaxies and do exactly the same thing to them and ask, okay, what is the distribution of mass that explains the lensing that we see in all those faint galaxies? And that's what you see here in blue. That's where the mass has to be located to give us the gravity that we see causing this. And you see, it's with the galaxies. Right? We actually do detect these clouds in this gravitational lensing as well. And they make up about 1/6 of the total mass. All right? So now we have something where we've taken away 90% of the normal mass, and we've shown that it only makes up 1/6 of the total mass. And therefore, we've now broken the problem that we had before. This can only be done with dark matter. So something has to be sitting there. It has to be causing the gravity which we're seeing, and it doesn't collide with itself because it stays with the galaxies during this collision. All right, so what can this be? Well, that's a little bit hard to say because unfortunately there's a lot of different potential particles that could do this. All right. I should also say this is only one cluster. You should never trust a sample of one because strange things can always occur anytime you have a single object by itself. So over the past 10 years, people have been looking at more of these. Here's another one of these. There's one cluster over here, one cluster over here. The X-ray gas cloud is again in red, right between the two. And the dark matter, or the gravitational lensing, is showing the masses again with the galaxies. There's some stranger ones out there. Here's a galaxy cluster that has some galaxies there. It has a core of galaxies there. It has a core of galaxies there. It has a core of galaxies there. It has some galaxies down here. It has some more kind of up there. These are all at the same distance from us. Instead of having two clusters pass through each other, this is something where we've had like 6 or 7 of these come through in the past billion years and hit each other. So this is effectively a train wreck rather than a simple collision. Again, the pink is the X-ray emission, and you can see that with the main distribution of galaxies sort of up here and down here, the pink is largely sitting between the two again, right? So we've had this collision occur, and the gas is offset. And the blue is the weak lensing, which is now distributed on much larger scales because you have galaxies just all over the place. But you can still look at sort of the patterns and see that the blue, that the weak lensing mass measurement, is in pretty good agreement with where the galaxies are and not in very good agreement with where the gas is. All right? All right, so what can be causing this is all sorts of what we call WIMPs. All right? When we first thought of dark matter and tried breaking it up into possibilities, one possibility is this could just be normal matter stuck into structures that are so cold that they just don't emit light at a level which we can detect them. These would be basically cold Jupiters and things like this. Those were called machos, or massive compact halo objects. The problem is those exert gravitational lensing. And you could go to look at observations of the center of our galaxy or some nearby galaxies, and certain stars should get brighter and fainter as these machos passed in front of them and did lensing on those starlight. And people looked long enough that they could convince themselves that it just doesn't happen. And so these cold Jupiters just cannot be a significant portion of what we see here. And that left the only other real possibility that people could think of were now things called WIMPs, which there's weakly interacting massive particles. They aren't predicted by normal particle physics, so you sort of have to add in some new physics to get them. But they are called weakly interacting because they do occasionally interact with matter. It's just on a very small scale. Right? So if they are WIMPs, we do have the possibility of detecting them here on Earth. And the way that you detect them is you basically build a very large tank of something. You put it someplace fairly isolated. And then dark matter, these WIMP particles, will periodically come in. For every few trillion which pass through, one of them might interact with one of the atoms sitting in your tank of stuff. And when that interaction occurs, you will get some energy exchanged. And depending on what is here, you either might ionize some electrons, which is what's happening in this diagram, is this interaction has freed up some electrons from the from the material. You have a field up here that's accelerating them upwards, and you detect them. All right? And so if you're sitting there, you basically have this thing that's hopefully doing nothing for a very long period of time. And then every once in a while, something happens, and you get a detection. And then you wait again, and nothing happens, and something happens. And you build this up enough times that you can say, okay, well, here's the interaction rate at which I have dark matter. And that allows us, within these models, to figure out what is the mass of the particle hitting it based on the energy which is released, as well as how many of these particles are actually going through and hitting it. The problem is you can't fully isolate something like this. And so there are other things. There's all sorts of radiation which can go in here and cause other problems. Right? And so if you look at sort of what these are doing, there's been about 10 of these experiments done so far, and there's money for about another 3 or 4 on even larger scales. The stuff that's sitting in here varies. A large portion of them are using xenon gas, which is one of the noble gases. They basically get all the xenon they can and they liquefy it. And so you have basically a liquid pool of gas sitting here. Other people use germanium crystals. One type used actually salt crystals, because that was the cheapest thing they could find. You typically stick these down in old coal mines to try to get them as far underground as you can so that the rock can filter out some things. But you still have radioactivity in the rock, and that sort of problem can cause things to come in here and interact and cause problems. And so as a result, the results from this, from all these different observations, is on this chart, which we have the mass of the WIMP particle that would be causing the interaction. And this is the relative cross-section. So how large of a target do you have when you send one of these through a bunch of mass? Right? So the smaller this number is, the fewer collisions you have for a given particle. All right? These colored circles are where our best models for what we think dark matter might be sort of lie. So there's one sort of the generic WIMPs over here, and then there's another way of doing this called asymmetric dark matter, which would lie over here. The yellow line is when neutrinos, those particles that we know exist and can detect occasionally, that's what they do when they interact with this tank of stuff. And so we just can't detect it if it's below the yellow line, because the neutrinos would basically interfere with the measurements, which can already tell you one problem. Part of our possible parameter space for dark matter is sitting in a region in which you cannot detect because of the neutrinos. Right? But most of it is still above it, so there's a possibility of detecting it. Now, like I said, there's been about 10 of these experiments so far, and one of the problems is that 2 of these experiments claim that they have a detection in that region. The other 8 collectively say nothing in this region and above can exist. So we have 2 that have a detection in an area that's completely ruled out by the other 8. All right, so what's going on here? Well, remember you have all these other things that can come in and interact, and so people have to build very complex devices to try to detect all these other particles as they're passing through and rule out those interactions. So what's likely happened here is either these 2 experiments failed and they got things through, neutrons or high energy photons or something of that order, that caused these interactions that they didn't detect, and therefore they have false positives. Or these guys have been way too extreme in rejecting things, even if they didn't detect that particle coming in. And so they got rid of all the possible signals. And unfortunately, we just don't know what the answer is. There are going to be some future experiments that are basically going to carve out this line here, right? But even if we completely fill up this entire space and don't detect anything in the end, that still doesn't rule out these models, because they're sitting below our detection, our minimum detection line. So if you guys have heard of the Higgs boson, which was a big thing last year, this was something that was happening also in particle physics, which was every year they would attempt to detect it. Every year they would fail. And so they would adjust the model so that it would be just above the current detection threshold, so they could argue to try again. Well, these models can get moved down. All right, so maybe in a few years we will get lucky and one of these things will detect it, and then we'll at least know the mass and the cross-section, which will give us a pretty good idea of what sort of particle it could be. But it's also quite possible that we're throwing all this money at something that's doomed to fail, because this isn't necessarily just the only way of creating dark matter. Right? There's, in the end, all sorts of ways of doing it and creating things that would never even show up on this plot. So 5 years from now, I'm cautiously optimistic that we'll know what dark matter was. That said, I think people were saying that in the 70s as well. All right. Dark energy. You'll notice I don't have a whole lot of time left. That's because there's not much I can say here. Okay? What is dark energy? Well, if you'd taken an astronomy course prior to sort of 1995, what you would have been told is that the universe is expanding. This is a consequence, again, of general relativity. And that when you are expanding and getting bigger, you're going against gravity. And so gravity is pulling back, and gravity should be slowing the expansion rate of the universe. And so if you go back and read, like, for instance, Hawking's Brief History of Time in its first edition, he says these are the three possibilities, right? And the only question is how much matter there is. If there's enough matter, the gravity can overcome the expansion rate, and you turn around and recollapse the universe, and it comes to an end at some point. If there's just the right amount of matter, then the expansion rate slows down but never quite gets to zero, but you basically approach a static universe that's not expanding as time goes on to infinity. If there's not enough matter, then you slow down the expansion rate, but it never comes to a stop, and so it keeps expanding forever. In 1998, people used what are known as type 1 supernovas, which are exploding white dwarfs. And they're very nice because they always explode at about the same luminosity. And so if we see one, we can measure how much light we're getting from it. We can measure what's known as the redshift, which is how much the universe has expanded since that light was given off. And from that, we can figure out how far away they are, which is actually something very hard to do in astronomy. When they did this, they discovered that actually not only are we not coming to, turning around and collapsing, we're not going to the critical universe. The expansion rate is continuing, and moreover, for about the past 4 billion years, the expansion rate has actually been accelerating. It's been getting faster. So gravity has to be slowing it. And so how do you have something that pushes it and gets it faster? So that's when we invented dark energy. All right? We inherited the dark name from dark matter. We call it energy because whatever this thing is that's causing this expansion should behave like an energy field, which means it's roughly constant everywhere across the universe. Unlike dark matter, it doesn't collapse down into gravitational potentials due to gravity. And it's basically pushing everything apart. Right? Possibilities? Well, there are a couple energy fields from physics that we need for quantum mechanics. One of them is called vacuum energy. And as we create more space, we should be creating more vacuum energy. So that's a natural source for this dark energy, because it's basically going to keep pushing things away as it gets created. Problem is, you take your best model of quantum mechanics and you apply it, and you ask, okay, well, how much pushing should be going on from this vacuum energy? And it's 10 to the power of 120 times larger than what we observe. So if this was correct, if our models for vacuum energy from quantum mechanics could be directly applied to general relativity, we would not see any other galaxies. They would have been pushed so far away from us by now that the light basically couldn't reach us. Our own galaxy would be disintegrating, and within relatively short times, our solar system would start disintegrating as well from the expansion rate. That's clearly not happening. All right. Other possibilities? Maybe we're wrong about gravity again. Instead of seeing an acceleration, maybe it's just not decelerating as fast as our gravity models predict. And so on very large scales, maybe gravity is weaker than it needs to be. Always a possibility. We're trying to figure out ways of testing for that. If you want more exotic possibilities, because we don't know much about dark energy, theorists are able to come up with all sorts of models. My favorite one, just in terms of what it does, is known as the brane world, which is a part of physics called string theory. Actually wants there to be 11 dimensions. The standard model of particle physics wants there to be 5. We have the 3 spatial dimensions, you have time as a 4th dimension, and to get the particle masses to work out, we need a 5th dimension that's rolled up on itself on very small scales, and so only affects things on subatomic scales, right? We don't experience it in our everyday lives. So if you need 11 dimensions for string theory to explain the universe, and we need 5 for the standard model of particle physics, then why don't we put 5 here? And let's put another 5 over there that we don't interact with, and that gives us 1 extra dimension to run as a string between the two. And let's just put some mass off in that other set of 5 dimensions that we don't interact with, and allow gravity to leak across the 1 dimension that connects us. That means that the dark matter isn't actually particles in our own dimensions that we could ever detect. It's mass off in that other set of 5. Interesting idea. It would also mean that we have no hope of ever figuring out what dark matter is. In terms of dark energy, well, these 5 dimensions can oscillate along the string, and you can have a interaction as they get closer and further from us, and that could actually drive the dark energy. Right? So you can get these kind of weird ideas, which in the end can't be tested. That's why I said you've sort of hit the fringe edge of science. We may or may not ever be able to know more about this. Right? It might be that our astronomy observations that say the dark matter is there in terms of its gravity might be the limit of what we're ever able to detect. And dark energy, well, we're trying to figure out ways of characterizing it so we can learn more about it. But right now, we really don't even have a good model to go after. But that's not stopping us. Right? So what is the future of all this? The future of this is we're changing astronomers into computer scientists, essentially. All right, this is a telescope that we're currently building. Just recently got approved by the federal government. It's going to be built down in Chile. It's called the LSST, and this is an 8-meter telescope. Just to give you an idea, that's a guy standing there. And the special thing about this telescope is the problem is usually we're looking at very small portions of the sky to look at these galaxies. We want to look at the entire sky very rapidly, but still be able to look at individual galaxies. And so to do that, we basically need a super camera, right? So if you buy a digital camera, you're buying usually a CCD chip, and they sell it in megapixels, right, for just the number of pixels. So, I don't know, typical ones used to be sort of 4 megapixels, and then they went up to 8. I think you can buy some 20 megapixel ones these days. Right, that's about 4,000 pixels by 4,000 pixels or so. In order to image the sky effectively, this camera has been built with this telescope so that we can have 0.2 arcsecond pixels. So remember, 1 arc minute is 1/60th of a degree. An arc second is 1/60th of an arc minute. The pixel is 1/5 of that. So if you take that sharpened pencil, you need to divide it basically in about 2,000, and then you get the size here. All right. So you take those pixels, and we want to cover about a 3 degree by 3 degree area, so that we can just sort of stare there and move and stare there and move and stare there. That means we need 3.2 gigapixels. All right. So basically, this is a super camera. It winds up being about this big across. And one of the hardest parts isn't actually getting the devices to detect it. Those can be made pretty clear. It's getting glass filters that are that big across and about that thin that can actually withstand their own weight when you hang them on this thing. Because if you deform the filter, then you do all sorts of horrible things to your images. But we think we've solved that now. And so this is under construction. It should be should be fully built by about 2019 or so. It'll then be tested for a year. The survey will start in about 2021. And the idea is for the next 10 years, we're going to make a movie of the southern sky in which we can cover the entire southern sky every 3 days. And so every 3 days, we get a picture of the southern sky. We can add up that data over 10 years, and we get the deepest images that we've ever taken over half of the sky. And that gives us now enough data to start looking at things like dark energy and distinguishing among models. Right? It's also going to do a lot of other things for us, too. So here's the current best big survey that we have. It's called the Sloan Digital Sky Survey. And relatively speaking, that's what it looks like over this patch of sky. Right? So you can see the big galaxies. There are some small galaxies in there, but you don't actually see a whole lot. That's what the LSST would be seeing, right, in terms of all of these additional ones, just because we have a much bigger telescope and expose much longer in the end. Right? That gets us basically down to these levels that we can start getting these 10 billion galaxies to play with. Yeah. Right? But it's not only going to give us stuff to go after dark matter and dark energy. It's also going to give us 1 million supernova. It's going to give us a bunch of these galaxy lenses to play with. It's going to give us 1 billion moving objects. And by this, we mean everything such as all the asteroids that might potentially hit the Earth. It's going to give us, in fact, it's going to give us pretty much all the asteroids in the solar system. It's going to give us stars that are moving relatively rapidly around us, so we can start characterizing how the Milky Way objects are moving much better. And whenever you do this, the most surprising thing and the best science that comes out is usually something that you didn't know when you started it. So we're also fully expecting that we're going to revolutionize astronomy. And 10 years from now, you will hear a completely different talk about dark matter and dark energy because someone will have found something that in our current data set we just can't detect right now. that's going to change everything. All right, so that's sort of what we're looking for. I should say that as a result, we're generating 20 terabytes of data per night. That has to get added up over 10 years. That will be stored all online. Google is very interested in working with this. So we'll have a Google universe, I think, at some point where people can look at that. And that's why I'm saying we're turning into computer scientists, because instead of going to telescopes and taking data, we're just simply going to be sifting through this archive for a long time to come to try to find things. Right, if you're interested in this, I thought I'd assemble just some of the popular books around. These are all sort of written at a sort of college level. These two deal with everything I talked about. This one is just on dark matter, and this is a special one just on gravitational lensing, if you're interested more about that. All right, thank you.
Okay, at this point, whoa, this one's going to work. Okay. Thank you, everybody, for staying, especially because we know that the volume tonight, we're still having problems with the speaker. Not the speaker, the speakers. But I wanted to make sure that you guys have an opportunity now to plug away at some questions. You guys have an expert up here. So what are some of the questions that you guys have for him? Make them hard. We have T-shirts. Anybody? Go ahead, scream it out. Go on.
Yeah, so for the LSST survey, the survey, what it is due to the size of that camera, is we're going to stare at a given place for about 90 seconds and then move by 3 degrees and stare at a place for 90 seconds and keep doing that. And that's how every 3 nights we can cover the full sky, right? So it's basically a third of the sky each night under that strategy can be filled due to the size of that camera and staring at it for that long. Yeah, and then we get it the full depth by just adding that data up as we start taking it and just adding the images on top of each other. Yeah. Yeah.
You've divided some of the mystery into energy and mass, or energy and matter, but
Right.
we know there's no distinction between the two.
Right.
Is it presumptuous to assign a value of 70% to one?
Well, okay, so the value comes from actually, here's where I have to break into equations. So the question is can we actually divide this up into 25% matter and 70% energy, given that we know from Einstein that energy and matter are the same thing? I should say that what we've really divided this up into is 2 different things. There's something that behaves like a massive particle, something that reacts to gravity that we find in these galaxy clusters and individual galaxies. There's something that doesn't seem to react to gravity, that only operates on very large scales. It's driving this acceleration of the universe. Are the 2 actually related to each other? It might be, and people do work on models that try to have that. It's kind of hard because they're on slightly different scales, right? One of them condenses down, the other one doesn't. But like that brain world that I was talking about with those extra dimensions, that actually solves both problems simultaneously, although you still have a separate set of matter and dark energy being something different. So our guess is they're probably 2 different things, but it might not be. And for that matter, we don't even know if dark matter is just one type of particle, right? You always try to go with the simplest thing in science. It could be 3 or 4 different types of particles that we haven't detected. It could be dark energy is actually 3 different fields. We just don't know at this point. Yeah. Yeah. Yeah.
What does the verification of the Higgs boson particle say to some of the things you're talking about?
Okay, so the verification of the Higgs boson, and how does it affect this? It really doesn't affect the dark matter too much. So the Higgs boson is really just a part of the Higgs field. So this is one of these energy fields that we're saying that we kind of knew needed to exist. And what this does is by particles interacting with the Higgs energy field, you add mass. But that mass is really only important for electrons and quarks. Protons and neutrons get most of their mass actually from the binding energy of the quarks holding each other together to form the proton and neutron. This dark matter particle, we don't know what it is. It might be something that interacts stronger with the Higgs field and gets its mass that way. That's one set of particle possibilities people try to investigate. It might have nothing to do with the Higgs field at all. In fact, there might be this extra energy field which it's moving in, which gives it mass And that's why it doesn't interact with protons and neutrons very much. So in the end, until we know more about sort of the mass and the cross-section for dark matter for collisions, we really can't start breaking it down into, does this thing interact with the Higgs? Does it interact with, well, we know it doesn't interact with electromagnetism, but that's about the only thing that we know. And what all these other fields could be. But the Higgs field is a good example of an energy field that seems to be everywhere the same across the universe. And so it also gives us a good model for what dark energy might look like. It would just be another one of these energy fields. Yeah. And there's a question back there? Is it possible that what's causing the expansion is outside? I mean, it's certainly the case that we can't see outside of it, but things also tend to move at about the speed of light. And so if it's outside of the universe, the chances of it being able to affect us isn't very great. So you could say that if our observations were based on things right at the edge of our field of view, then yes, certainly things outside, because they could affect that without affecting us yet. That could be causing it. But mostly what we're seeing in dark energy, for instance, is things that over the central part of our bubble, out to things that have been moving about 4 to 5 billion years, seem to be affected by this. Things at larger distances, the dark energy seems to be relatively unimportant, which actually might be giving us a clue that it might be a local phenomenon, meaning only over 4 billion light years, rather than a more global thing over a larger size. So yeah, that's other possibilities people look into, is instead of a steady energy field everywhere, something that might just be affecting us. Yeah, I think his hand up. Yeah.
What stops us from seeing beyond what the visible universe? Like, what stops?
What stops us is just simply time. It's light travels at the speed of light. And so if something is outside the observable universe, it's just because there hasn't been enough time for that light to reach us. And the reason why we only have a certain amount of time is because of the expansion of the universe. Right? If we go back to this slide, right, we know the universe is presently expanding. We can measure it. You just follow it back in time. We can measure it to about that point. And then presumably it keeps expanding behind the point at which we can measure it. And that has everything basically coming back onto this point, which is where we get this whole Big Bang idea. We don't actually know that that occurred. We know that it went up to about there, right? And what happened before there is a bit of a mystery. We have some clues from other branches of physics, but we don't know if the universe actually began there. Did it start expanding out of an older universe? Those are some other mysteries that we just don't know because we can't observe that far back. All right.
Okay, one more question.
Okay. Yeah.
Do we know roughly where the universe is expanding from?
Ooh, Astro 1000 is a great class to take. Where is the universe expanding from? Actually, you don't, because if we take our position and we look at all the galaxies around us, they all seem to be moving directly away from us. And therefore, they seem to be expanding as if we were at the center of the universe. But you can also move your position and say, okay, well, what would that galaxy see? And that galaxy would also see everything moving directly away from it. And the reason for this is the galaxies aren't actually moving. What's happening is space is stretching. And so if there was, a light, or I shouldn't say light years, if there was 1 million light years between us and that galaxy, over time, that distance is going to increase. A galaxy that starts twice as far away will have its distance increase twice as fast because space is stretching the same everywhere. All right, so you now reverse that and say if space is stretching the same everywhere, you go backwards in time, everything starts going back onto the same point. The hardest part about cosmology to try to get across from people is that the universe isn't expanding into space. The universe is space, and it's just getting bigger. And so prior to this point, one of the problems with understanding the Big Bang is if it actually occurred, the universe exploded into nothing. I mean, literally, there was nothing there, and then the universe began, and this universe instantly was everything, including space. So, yeah, like I said, it's kind of hard to understand this. I always tell the students when they're taking this is, if you really want to understand the way the universe expands, you pretty much have to take about 6 or 7 courses in it, and then do a bunch of research, and then hope that inspiration hits you. There's a lot of people, including myself, who just intuitively you can't really think about this because it's so different from what happens to us here on Earth.